which is almost stationary. But what happens is the electron will be going in this direction, and the anti-neutrino will be going in this direction. Okay, so the summation of all these positions, this will go a bit this side, not much. Okay, so basically when we are considering the angle, if you are considering this angle total between electron and the antineutrino that is being formed here, okay, if you consider omega e and d omega nu bar over it, okay, for all the particles that are being emitted, it will come down to 4 pi. Okay, so in that case our equation will become, so just 2 pi is here, you multiply it by 16 pi square, so you got 32 pi cube, and the remaining expression remains the same. Okay, so now you can just simplify it, and it makes a more easier form to take care of. Now this expression, it gives you the transition rate for an electron emitted in the momentum range PE and DPE. Okay, so basically what happens is, this is your transition probability for a single electron, okay, which is emitted with the momentum PE. Okay, and the change in momentum must be small, dPe. There may be other values also available, which we have not taken into account. Okay, so for that, if you want to take that into account, you have to take an integration over it, so which we will do later. Right now we have not taken into fact that which would affect the energy of the beta emission. Okay, so we have not taken one more fact into consideration, and that is the Coulomb interaction. See, when initially the nucleus is present, okay, at that time the interaction between the particles is inside the nucleus. Once beta decay takes place, the electron and the antineutrino is emitted outside, and the daughter nucleus remains there. But what happens is that once the electron is emitted out, electron being a charged particle and negatively charged particle, it will be attracted by the nucleus, because nucleus is a positive charged particle and electron is a negative charged particle. As a result, there will be a Coulomb interaction between the two. Okay, and since they are oppositely charged particles, the interaction is attractive. So even though initially the electron is emitted with high energy, what happens is that because of the Coulomb interaction, the energy of the electrons will decrease. If instead of an electron, a positron was emitted, then there will be a Coulomb repulsion, and as a result the positron emission would be with very high energy. So that is what we are going to see here. The beta particle must experience the Coulomb force after emission. The energy, the nucleus with charge Ze will accelerate positrons and retard electrons. Because electrons are opposite charge, the nucleus will try to pull it back to itself, and as a result the speed of the electrons will decrease. Okay, so it basically they get decelerated and the energy is also reduced. This implies that we shall have more electrons of low energy and more positrons of high energy than those predicted by this equation. So what the equation is, what I'm trying to tell you is that the transition probability and the electrons being emitted, which is predicted by this equation, okay, they will be if it is electron, it will be less than this what is predicted by this equation, and if they are positrons, then they will be more than which are predicted by this equation. Why? Because of the Coulomb interaction. This will get reflected in the beta spectrum. Fermi computed this Coulomb correction. This has to be incorporated into the equation. We may write it as FZE. This part is added into the equation. Okay, this is a Coulomb correction that takes place, because after emission only the Coulomb force will take place. Before emission the Coulomb force was not taken into consideration, because at that time it did not apply to the electron. Okay, so once it is the electron comes into existence or a positron comes into an existence, only then does this force the Coulomb correction takes place. Okay, the function FZE is called the Fermi function. Okay, and its sign changes depending on whether it is applied to electrons or positrons. Okay, so this function is called the Fermi function. Okay, and its sign will be positive or negative depending on whether it is electron or positrons. Here it's not mentioned that whether it is positive for electron or not. Okay, so it can be any sign. Okay, here there is a graph is being shown. Just let me reduce it a bit. This graph is being shown. Here is the energy scale and here is the Fermi function. Okay, this Fermi function, it depends on the what you call as the Z or atomic number and the energy of the electron emitted. Okay, we shall discuss this function properly. So here Z is taken negative for positron emitters and Z is taken negative for positron emitters and positive for electron emitters. We see that low energy electrons are more favored in comparison to positrons. Okay, for Z is equal to 0, FZE is equal to 1. When you are having Z is equal to 0, your function F, okay, your function F will be 1. Okay, so this is the value for 1. So what they are saying is that from this figure we see that low energy electrons are more favored in comparison to positrons for Z is so. Okay, now here the negative is for positron and positive is for electron. So these positive values are for electron. So we see that for Z is equal to 1 case scenario. Okay, actually it is Z is 0 here. Okay, Z is 0 here. For this case, if you consider this as a boundary, in that case we can see that the positron this values, positive values are more and negative values are less. Okay, so the more positive values are associated with electrons and the less negative values are associated with positrons. So what it is trying to say is that the Coulomb correction that we have added is actually a valid assumption, and it has to be taken into consideration when deriving the theory. Now also these calculations have been done to include the screening effect of orbital electrons in Fermi functions. So okay, now all of this is you have derived the theory and you have obtained the expression, but how do you compare it with the experiments to verify it or justify it? Okay, so what we do is, you remember that our expression is of this form: dWFi is equal to 1 by 2 pi h cut raised to 7 c cube, and then we have the expression for the matrix element, and then there is an energy component available to you. Okay, so what we'll do is, if we take this part and this part, okay, all these three, if you take it to the left hand side, that is divide dWFi by 1, 2 and 3. Okay, in that case what is left is okay, obviously, and we have to take into consideration the Fermi function also. If you take this 3 and divide it, dWFi is divided by 8. Okay, and then we get a constant, we get the matrix element, and then we get the Emax minus EE. Okay, note that here they have taken a square root because E minus Emax is a square, so the square term is removed. Here it is 1/2 and inside is a square, and dWFi is also raised to 1 by 2. Okay, so if you write it in this form, what kind of information can you obtain? The LHS of this equation is determined experimentally and it is plotted against the measured electron energy EE. Okay, so we know the value of Emax from experiments also and from theoretical calculations. Okay, EE is the electron energy which you can measure with your counters. Okay, so once you measure EE and you find dWFI by F PE square dPe experimentally, you can plot a graph. Okay, if you plot a graph based on this equation, it should be a straight line. Okay, so here they explain it in more simpler manner. The LHS of this equation is determined experimentally. Okay, so basically this section is determined experimentally. Okay, and it is plotted against the measured electron energy. So this is measured experimentally, and we know this from also from experiments only. So both of them are available to you. You plot a graph. Such a graph is expected to give a straight line, that is y is equal to mx. Okay, provided that the matrix element does not depend on momentum. Okay, this equation is true only when this part p square dp, okay, and f, they do not depend on each other. If it depends, then it will not become a straight line, it will become a non-linear equation, or it may show a different relation. But generally that is not the case. We expect the matrix element to be momentum independent, because for most beta decays, if it were to change from decay to decay, then to understand the interaction responsible for beta decay would be a difficult task. Okay, so if your function, or if your momentum matrix element changed from for each decay of each different element, in that case we will not have a proper consistency. Okay, and if we didn't have a proper consistency, then to understand the relation or to understand beta decay would be a difficult task. Our assumption here is that the operator HW is applicable to all beta decays. Okay, now K equal to dWFI F upon PE square dP whole stop is called the Curie function. Okay, what is it called? It is called the Curie function K. When K is plotted against EE, we get what is called a Curie plot or a Fermi plot. Curie plot or Fermi plot. Experimentally, the transition rate dWFI. So now what is dWFI? Experimentally, if you want to measure dWFI, then it is the number of beta particles per energy interval. Okay, so what does this mean? Say, hi, they are explaining it. A Geiger counter. All of you are familiar with the Geiger counter. Now, when you're using a Geiger counter to measure alpha or beta particles, normally what we do is we note the number of particles. Okay, how many counts are there? But we are never paying attention to the energy of the particle. Okay, so what we can do is using Geiger counter, we can count the number of particles. Okay, and the energy of the or the momentum of the particle can be found out with a magnetic spectrograph. I hope all of you remember that we had studied beta ray spectrograph in the 4th semester. Okay, in that we use the magnetic field. We applied magnetic field to the electrons, and as a result, according to their energies, they fell on different spots depending on their energy and formed different circles, different semicircles. Okay, so based on that we determine their energy and their momentum. Okay, so if when the beta decay is taking place and if you use a magnetic spectrograph, you will find their energy and momentum, and if you use the Geiger counter, then you can find the number of particles. So using this two information, you can find the number of beta particles per energy interval. Okay, so what does this imply? It is that the number of beta particles per energy interval. Let us say, supposing I have an energy interval from 1 electron volt to 2 electron volt. How many electrons are there, beta particles? So I will ask a question. If the energy of the if I consider an energy range from 1 electron to volt to 2 electron volt, how many beta particles are emitted? Note down the number: from 2 to 3, how many beta particles, 3 to 4, how many beta particles, and so on. That is what it means, the number of beta particles per energy interval. For a particular energy interval, how many beta particles are present. Okay, that is here what DWFI means. The Curie plot is found to be a straight line. Okay, over a wide energy range. So everybody is clear about this? Any questions, queries? Okay, to understand the Curie plot, we are showing there are three graphs here. Okay, this first is graph for tritium. The second graph is first graph is for neutron decay. First graph is for neutron decay, second graph is for tritium, and third graph is for cobalt decay. So based so if you notice this curve, okay, if you notice this curve and this curve here, you will see that when you are considering that the mass of electron of the neutrino is non-zero, the curve will change slightly only. Okay, and based on this we are able to determine the mass of the neutrino. So experiment results of data of this type puts an upper limit of about 200 electron volt to the neutrino mass. So basically this is very old information. So 200 electron volt is a very small value for mass. Okay, so I checked it out on so I found that current estimate for neutrino mass is about 0.12 electron volt, 0.12 electron volt. So that is roughly around 10 raised to minus 37 kilograms. Okay, so it is 10 raised to minus 10 times the mass of what you call proton. Okay, so that much lighter is the neutrino. That is the estimate, current estimate. It is around discovery of 10 raised to minus 2 raised to 2019. So the neutrino mass is almost 0.12 electron volt. Okay, recent experiments have lowered this limit to 46 electron volt. Okay. As predicted by the Fermi theory, the Curie plots are straight lines and the intercept on the energy axis gives the endpoint energy Emax. So this intercept will give you the endpoint energy of the electron. Okay, for beta decay. Thus Fermi theory is quantitatively able to account for the form of beta spectra. Notice that for low energy electrons, the points of figures A, B do not lie on the line. Okay, so here there are some points which do not lie on the line. Okay, that is because this division is due to window thickness of the beta counter. A Geiger tube which is about 5 milligram per centimeter square, and it is enough to absorb the low energy electrons. Okay, so basically there are some points which are lying outside, but this is what these are due to the window. The Geiger counter which is used to detect has a window which is thick as 5 milligram per centimeter square, and as a result it will absorb some of the electrons. So these electrons are never detected. As a result we have some outliers also. Also, the part B of the same figure shows the change in Curie plot with a non-zero rest mass for neutrino. The experimental data leading to Curie plot enables us to put an upper limit on the neutrino rest mass. Okay, so basically so this figure is mostly connected with the mass. If you assume that 0 keV means the rest mass is almost zero of the electron, then you get almost a straight line. But if you assume a 0.25 keV, then also it is same. But if you assume that the mass of electron is about 1 keV, then there is a slight change in the curve of the Curie plot. And so based on this curve information, we can determine the mass of the neutrino. As remarked earlier, the matrix element of the Fermi theory, being momentum independent, does not influence the shape of the beta spectrum. Okay, so this almost matches the shape of the beta spectrum that was emitted, shown in the first time when the beta spectrum was discussed. So this shape is mainly due to the phase space consideration, which leads to the Curie plot. The beta spectrum shape thus cannot give us information about the interaction which brings about the beta decay. It is possible to get an idea about the strength of this interaction by considering the lifetimes of beta emitter. So basically what is happening is, we discussed that the density of the states gives you the shape of the beta spectrum. So this shape is due to density of states, so that we have obtained. But in our expression we have the element of matrix element FHWI. Okay, there is no information. How do we get information about it? Okay, from this expression or from the graph. Okay, there is no, because it is generally constant, so we cannot obtain such information from it. So to get the information from it, we have to consider the lifetime of a beta decay. Okay, so we'll go to the next section about lifetime of beta decay. Now does anybody have any queries with respect to all whatever is being covered right now?
No.
Hello?
Sir, hello.
Yeah.
Question 20.
જ્યારે આ એમિશન થયું પ્રોસેસ આપણે કેલ્ક્યુલેટ કર્યું કે પાર્ટિકલની એનર્જી કેટલી છે, બરોબર છે, અને શું કહેવાય કે એ કઈ ડિરેક્શનમાં જવાનું છે, એ કેટલી એનર્જી સાથે આવે, કેટલા પાર્ટિકલ્સની કેટલી એનર્જી હશે, ઇન જનરલ આપણે પ્રિડિક્ટ કરી શકીએ છીએ, બરાબર છે, બીકોઝ ઓફ ધ કેલ્ક્યુલેશન ઓફ ટ્રાન્ઝિશન રેટ. ઓકે, બટ હવે there is another element આખા ઇક્વેશનમાં હતો કે the transition from final state, means initial to final state માં જે ટ્રાન્ઝિશન થાય છે એ ઇન્ટરેક્શનના કારણે થાય છે. એ ઇન્ટરેક્શન છે આપણે કહીએ છીએ વીક ઇન્ટરેક્શન છે. તો વીક ઇન્ટરેક્શન કેટલું વીક છે, એની એનર્જી શું છે, એની પ્રોપર્ટીઝ શું છે, બરાબર છે, એની કોઈ ઇન્ફોર્મેશન આપણને બીટા સ્પેક્ટ્રમમાંથી મળતી નથી. તો એ ઇન્ફોર્મેશન આપણે ક્યાંથી ઓબ્ટેન કરી શકીએ? From where can we obtain the information about the strength of the interaction matrix? That is the question. For that, what we will do is we will integrate the dWFI. Okay, dWFI is transition between one state and another state. Okay, so but this is only for a fixed momentum rate. This interaction, okay, was for an electron with energy Pe only. Now for all the electrons, or for all the complete range of momentum, you have to integrate over momentum. Therefore W is equal to from zero momentum to maximum momentum for dWFI. Okay, so in this case again your expression, this is a constant, so it will come out. This is also a constant independent of momentum, because we have assumed that matrix element is independent of momentum. This term is outside. So now the integration takes place over what? Your Fermi function, momentum, energy, momentum, and change in momentum. Okay, now the total transition probability W, okay, that is for a particle to make a transition, it is inversely proportional to the lifetime. Okay, lifetime, mean life of a particle. Okay, W is inversely proportional to the mean life of particle. Okay, I hope all of you know what is mean life of a particle. Okay, I'll just briefly mention it, that if you know about half-life, Half-life is when the original content is made half. The amount of time in which the original content is made half is called the half-life. But mean life is what? If you consider lifetime of each and every particle. First beta particle, how much time did it survive? Second, how much? Third, fourth, fifth, sixth, all these particles. The time taken by all of these particles, you add it up and divide by the number of particles. So it will get a mean life of a beta particle. So that is what is called tau. Okay. Thus, an idea of the magnitude of matrix element can be obtained by evaluating 4.24. It is very easy to evaluate this for small z and large energies. Okay, so this expression is simple to solve if we consider z to be small and the electron energies to be very large. In this when you consider this combination, the value of f is almost 1. So you can totally forget it. If you forget this term, okay, if this is made equal to 1, okay, so now your integration is only over p square e max minus e whole square dpe. Now e max minus e whole square, this is also a constant. Okay, and pe square can also be written as a difference of e max. So you can easily get, on integrating, some constant multiplied by e raised to the 5th power of maximum. Okay, so what you get is the RHS is a function of E max. So this value of E max is already known to us. Okay, it is possible to evaluate the integral in 4.24 accurately, and in general we can write. Okay, so this was a solution that is obtained when you are taking f is equal to 1. Instead of that, so if f is 1, then we know that the value is proportional to e raised to 5th power of E max. Okay, so instead of that, now if we take a general value of f, in that case the answer comes out to be m e raised to 5 c raised to 7 f. Okay, where m e is the mass of the electron. The function m e raised to 5 c raised to 7 is put to make the is used to make f dimensionless. Okay, and this function f is a function of E max. Here it is a bit blurred, so what we are doing is we will substitute this value integration in here. So what we'll get is we'll get some constant into f h w I, okay, is equal to 1 by tau. So w is equal to 1 by tau is equal to m e raised to 5 c raised to 7 f 2 pi cube h cut raised to 7 c raised to 7 f h w I whole square. Or you can write that f h w I is equal to 2 pi by 2 pi cube h cut raised to 7 f tau m e raised to 5 c raised to 4. Okay, so an estimate of the matrix element responsive for beta decay can be made if we know f into tau, because all the other components are known to us. H is the Planck's constant, me is the mass of the electron, c is the speed of light, and 2 pi is 2 pi. So all of this is known. Only f into tau, if we know, then we can find f into I. Again, tau is an experimentally measured property. The function f is calculated. It is more common to use f tau half, or f tau is called the comparative lifetime and f tau half is called comparative half-life. Okay, if the matrix element is same for all beta emitters, then it implies that they will all have the same f tau value. Okay, so first we know this value. Now what they are saying is that f into tau, in this tau is already experimentally known to all of us. Okay, so since this is common for all emitters, okay, there it is called the comparative lifetime. Okay, so basically depending on the type of element or element, f tau may be different. So we can say we are comparing, they will have different lifetimes. So using ft we can compare different elements, and so there also one more term ft one half. So it will be comparative half life. Okay, it is same as half lifetime only. It is similar in concept. Okay, the reason why ft is called comparative life is time is compares metric elements of beta emitter. So you will basically use f tau to compare different beta emitters. Okay, actually a wide variation ft values is observed from about 10⁻³ to 10⁻20 seconds. So lifetime of beta emitters can vary from 10⁻³ seconds. Okay, 1000 seconds to 10⁻20 seconds. Now we know that the value of the matrix element will depend on the wave functions of the nuclear particles involved in the beta decay for the initial and final state. The interaction apparatus H. Okay, such a tremendous variation in Ft can, now we know that the matrix element FHWI, okay, this value ranges from 10⁻³ to 10⁻20. Now this is a very large variation. So also the states are fixed, final, initial and HW, all of three of them are fixed. So why is this variation taking place? The observed large change in Ft values must then come from the nuclear wave functions that enter the calculation of the matrix element. Okay, such tremendous variation in Ft values one can hope to understand only if the interaction is universal for beta decay and does not change from decay to decay. Now all of this large variation, they can be easily understood if the interaction is universal, is same for all of us, and the difference comes only because of the wave function. Okay. Fermi was able to show that this is indeed the case. In general, the most fundamental beta decays, those corresponding to low z, give rise to largest matrix elements and therefore the smallest Ft values. For example, decay of neutron to proton, electron, and antineutrino has a half-life of about 11 minutes and Emax of about 0.782 MeV. It gives an Ft half equal to 1100 seconds. Okay. We can estimate the matrix element corresponding to this fundamental decay. So you can write down this, substituting all the values, you get Ft one half, which is equal to 1100 seconds by log e raised to 0.693. So it will give you 1587 seconds. Substituting this Ft and taking square root, it gives you 2.7 10⁻⁻⁴ mega electron volt Fermi cube. As marked in the beginning, the matrix element gives an energy times volume. Okay, so this is energy into volume. The volume of the proton, which is about the product of decay, can be estimated from 4.1.6. This is about 1 Fermi cube. Thus, the interaction energy responsible for beta decay process, which is distributed over the proton volume, is of the order of 2 into 10⁵ mega electron volt. Okay, so since the value of H is so small, it is almost like 200 MeV only. This is the reason why beta decay is called a weak interaction, and we are quite correct to use the perturbation theory in quantum mechanics to calculate the transition rate. Okay, I think this part is more of a descriptive term, but basically what is happening is that we have to find the energy matrix HW. Okay, so for this we find the total transition rate, which is inverse of the mean lifetime. We calculate and solve this term and obtain the value, and we get an expression for the matrix element. We compare it, we substitute one of the experimental results, and we find that the value of this interaction is around 2 × 10⁴ mega electron volt. Okay, so that is why it is called a weak interaction. Also, the energy associated with the mass of proton. For single mass of proton, the energy is 10⁵ MeV, whereas this is 10⁻⁴ MeV. This is due to the nuclear interaction. This is why the nuclear interaction is termed as a strong interaction. The weak interaction is smaller by a factor of 10⁷. Okay, so I'll stop here. We will continue next time with